Alrighty. So we are going to be talking about probability here. And first we want to talk about our definition of probability. Probability is the likelihood that an event will occur. Essentially, it is a measure of chance. It is our way of taking chance or luck in some ways and making it a measurable mathematical idea that we can reference back to and include in what we're doing. Okay, so there are two different types of probability. The first one is called theoretical probability, and our other word for it is statistical. So you might hear me say statistical probability. This is what should happen. Kind of like a prediction. Okay? These are the things that before something even happens, we have mathematically, so a prediction using math. We have mathematically predicted, okay, if I have a coin and it has two sides, the chance of flipping a heads is 1 out of 2. Okay? If I roll a dice that has 6 sides, the chance of rolling a 2 is 1 out of 6. Okay, that's the statistical or theoretical, what we think should happen. The other type of probability is called experimental, and our other word for experimental is empirical. An empirical probability is what actually happens okay? It's what actually happens. It's our probability of when you run an experiment, what do you actually end up getting to happen? Okay? Now, how do we find probability? Well, the first thing I want to note is that this fraction bar here is a fraction bar, and fractions mean division. So we are going to use division in our work. Okay? The thing that goes on the top is the number of our desired outcome. Occurring. I'm running out of space. Okay, so how often does what we want to happen actually happen? And sometimes what we want to happen, we don't actually want it to happen, but it's what we're measuring. So we call it our desired outcome. On the bottom is the number of total outcomes. Okay, so if I'm thinking about rolling a dice, rolling a 2, there is one side of a 6-sided die that is a 2. So my desired outcome is 1. Because one side is a 2. There are 6 total sides of the die. So it's not about when I say the desired outcome, you're not actually saying what number on the dice you want. You're talking about how often can that happen. Okay? Number of desired outcome occurring over the number of total outcomes. Now we use a specific notation. We use the probability, and then we write whatever event it is that we are measuring. Okay? We write whatever event we measure. Okay? So, what is the probability that a person in this class has a birthday on an even day? I'm taking the probability, big capital P, to tell us probability, and we want even birthdays. So I'm going to use the word even, not event, even, to indicate that we are looking for even birthdays. That's our desired event. Even birthdays. Okay? Well, let's think about what that could be. On the top is going to be the number of people with an even birthday. And on the bottom is going to be the number of people in class. They are the people we are asking So they are like the possible outcomes. Okay, well, say I have a class of 10 kids and 6 of them have their birthday on an even day, on a 2, 4, 6, 8, 10. Then my probability would be 6 out of 10 for a probability of an even birthday. Okay, within theoretical and experimental probabilities, we have different types of events that we measure. The first type of an event is called an independent event. An independent means by itself. So what this means is that the probability does not change depending on what happened before. A really good example of that is flipping a coin. Okay, whether or not you land on heads or tails, you're still gonna get an even 50-50 chance the next time you do it. So what happens the first time doesn't impact what happens the second time. Our key phrase that we have here is with replacement. Okay, if you think about a raffle where you have an opportunity to win a prize, oftentimes with a raffle, they will take out your name once you win from the bucket, or the winner's name out of the bucket. And the reason they do this is so that the fact that you won before eliminates you from the chance of winning again. That is dependent. They are saying because it happened the first time, your probability was good the first time, you are now taken out of the possibility for the second time. If they put your name back, that would be independent, because it's giving you a chance. It's saying it doesn't matter what happened before, you still have an even shot. So if independent is with replacement, dependent is without replacement. We are not putting back the card in the deck. We are not putting your name back in the pile. One example I really like that someone gave is genetics. The probability of you inheriting certain genes that maybe determine your eye color, your hair, things like that, are determined by the probability that came before you. If both of your parents had a really low chance of having blue eyes, a kid with blue eyes, and you don't have blue eyes, then the chance that you then have a kid with blue eyes is low, because what came before you impacts what comes next. Okay, so genetics is one. Another is a raffle, where they don't put that card back without replacement. So dependent is where the probability changes depending on what happened before. I want to be very clear that this does not mean that the situation can't change. Often the situation will change. The probability of something happening and then circumstances change, and then its probability changing is high. That can happen. We want to be mindful of, am I measuring the circumstances changing, or am I measuring, the probability of it happening changes? So just be mindful of what is changing if you're being thoughtful of that. So some examples for you. The first one is if I am pulling an ace from a deck of cards. So my theoretical probability is the probability of an ace. Okay, well, I know that there are 52 total cards in a deck, and 4 of them are aces. So that is my theoretical probability. Okay, if I were to divide this out, I would find that I have a percent chance of 77% chance of pulling an ace from the deck. Now here I'm going to run this experiment. I'm going to actually find a deck of cards and draw a card out. And when I did that, there were 52 cards in the deck. And I'm just pulling one. And it was not an ace, it was an 8 of spades. So that would mean I got 0 of my desired outcome. Well, if I look at that percentage, that says there is a 0% chance of ever getting an ace. Now, is that accurate? Probably not. But in this experiment, that's the probability that it's sharing with us. Okay, so theoretical and experimental will not always match. In fact, rarely do they match. What I can tell from this experiment is because I'm only pulling one card, and because there were all 52 cards in the deck, it is an independent situation. There was replacement of whatever came before, so the chance is not impacted by what happened before. Next situation is the probability of a coin landing on heads. Well, theoretically, the probability of heads is equal to the number of heads on a coin over the number of sides. Okay, well, there's one side that has heads, and there are two sides of a coin. So my probability is 1 out of 2, or 50%. Experimentally, okay, I got my coin, I flipped it, and I got it. Okay, so of the two sides, I got it. Beautiful. Okay, so that says that I have a 1 out of 2 chance, or a 50% chance of getting it. Sweet. We got 1 out of it, and in this case, it does match. Again, we have an independent situation because the coin is not influenced by what happened before it. Finally, what the probability of a given day of the week being a weekend. Okay? I like to think of this as drawing a day card out of a hat. Okay? If I'm drawing a card that has days of the week on it, written on cards in the hat, what is the probability of it being a weekend? Okay, well, theoretically, my probability of a weekend, I'm going to use capital W, capital E for weekend, is equal to the number of weekend days over the total days. Okay, well, I know that there are 2 weekend days, Saturday and Sunday, over 7 total days of the week. So there's a 2 out of 7 chance. If I run this experiment, okay, or I pick a random day, is today a weekend? Well, I'm at school, today is a Thursday, so no, it is not a weekend. So the number of desired, we didn't get any of my desired, so it's 0 out of 7, which means that there is a 0% chance of it ever being a weekend. Oh my gosh, I sure hope not. Okay? What is important to note with this is that this is still an independent situation because I said a given day of the week, not today, or not necessarily today. This just means in general, if I were to pick a name out of a hat, pick a day of the week out of a hat, the chances of it being a weekend are not determined by what happened before unless I take that name out. So it is an independent situation. Now, if I said that today is, then it would be impacted because you can only get 2 weekends in a row before you get to a weekday. So then it would be dependent because what happened the last 2 days is going to change your chances of what happens today.